This is 9.8, part 2. Alright, so last time we left out example 4 because I didn't have room to fit it in, so I'm ready to look at that one now. So this one, we're going to find the interval of convergence. And by the way, whenever you're finding the interval of convergence, you can find the radius of convergence along the way. So we'll be identifying what that is, even though the directions don't ask for it. We are going to find the radius of convergence. All right, so here's our series. If I use the ratio test, take the limit as n approaches infinity of the absolute value of that expression behind sigma with n plus 1, replacing every n, divided by that expression behind sigma as is. One of the things I'm going to do is rewrite this as this division of two fractions using the definition of division as the product of the numerator fraction and the reciprocal of the denominator fraction. And dividing the powers of n, x to the n plus 1, divided by x to the n, leaves x. And that has to stay in the absolute value because we don't know if x is positive or negative here. But the n over n plus 1 can be taken out of the absolute value because its n, remember, is 1 or bigger, generally speaking. So that's never negative at any rate. And so as we've seen before, the limit of the absolute value of x is going to be absolute value of x because it's a constant as far as the limit is concerned. And as n goes to infinity, n over n plus 1 goes to 1. And so that limit ends up being absolute value of x. Now, what we do with that is, because it's the ratio test, we know that that limit will have a convergent series as long as that limit answer is less than 1. So that means that we know that this is the preliminary interval of convergence, and we have to test the endpoints. But as I said earlier, right here, this expression is in that form of absolute value of x minus a constant, where our constant here is 0, less than r. When we have that expression, we can identify r, and in this case, it's 1. So what we're going to do is next test the endpoints. So if x is negative 1, then our series will become negative 1 to the nth over n. And if you think about that for a second, that's a series you should know. Has a name. Do you remember its name? It's a hint. It's the alternating harmonic series. And so if you remember that's its name, and you remember that it always converges, you can just state that. Or if you forgot all of that, you could just do the alternating series test and conclude that it converges. A little bit more. I see I made a mistake and probably was trying to talk and write at the same time. So let me fix that mistake. It's the alternating. I don't know what that last letter was supposed to be. Certainly wasn't what I wanted it to be. So let me squeeze in the n and the g. The alternating harmonic series converges. So we know we have convergence when x is negative 1. Then when x is 1, the series will become n equals 1 to the infinity of 1 to the nth over n, aka 1 over n, which is the what series? Right, it's the harmonic series. And we know that it always does what? It diverges. So this time, with an interval of convergence of a preliminary interval of convergence being everything between -1 and 1, we've determined that at -1 it actually does converge. So when we write the interval of convergence, we'll include the -1, but at x equals 1 it diverges, and so we don't include x equals 1. And there's our interval of convergence. And that again was example 4. Okay, so number 5 is what we did at the end last time. So I'm going to skip over that one because we already did it. So going on to the next page. Theorem 9.21. Properties of functions that are defined by power series. If you have a power series, f of x equals a sigma of some constant formula like a sub n times x minus c to the nth, which expands as you see below there, it will have a radius of convergence of r greater than 0, or when it does, then on the interval from c minus r to c plus r, f will be differentiable and therefore continuous. Moreover, the derivative and antiderivatives of f are as follows. I want you to take those statements somewhat with a grain of salt, because it appears that when you look at f of x, it starts at n equals 0, and then you look at number 1, f prime of x, it says that it changes to n equals 1, and that's not necessarily always true. And we're going to find out how to make sure what that starting value is. Is it staying 0? Is it changing to something else? And number 2, it looks like it's always going to stay from n equals 0 to infinity as well, and that may or may not be true. So we're going to figure that out as we go. Notice that they put the c in front of the series, because otherwise that plus c would be part of our sigma formula. And so instead of saying sigma stuff plus c, we write the c plus in front, and that takes care of that. Because otherwise, if you expanded the series as they did, when you have plus dot 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 plus c, that would mean it stops. And we want an infinite series. So that constant has to be written in front so that it doesn't look like we have a finite series. The radius of convergence, when you find the derivative or an antiderivative of a power series, is the same as the original power series. The radius of convergence is the same. But the interval of convergence, however, may be different, because you may gain or lose one of the endpoints as a convergent value. So you have to, again, if you do the derivative, for example, or the antiderivative, the radius of convergence, like this last one, would be basically -1 to 1 to start with, but then you'd have to test both endpoints, and it could be that you lose or gain one of those endpoints as we go. So let's do an example, because a lot of that will make more sense through the lens of examples, I believe. So let's say that we have a function f of x defined as a series from n equals 1 to infinity. And if you looked at the definition or theorem 9.21 very closely, you'd say, wait a minute, this one starts at 1, their f of x starts at 0, and that doesn't work. Well, yeah, it does. That's why I'm saying don't worry too much about what n starts with until you're writing answers. And then I'll show you how to figure out for each problem what the starting n value needs to be. So if we expand this putting in 1, x to the first over 1 is x, plus x squared over 2, plus x cubed over 3, plus, and I would suggest that we have at least 4 terms of that series, and I'm going to ask that you write it out for the first few terms so that we see the expanded version, because that's going to help us figure out what we're supposed to be doing. Okay. Now, this one was a problem that we did earlier. Let me see if I can find what number that was. It was a while ago. Or was probably in the other earlier video. Oh wait, I'm sorry. It was example 4. It's the one we just did. Okay. So that series we already know. Just look up here. That for that series, that one right there, it's the same one we're working with. We already know the radius of convergence is 1, and the center is 0. So the center is 0, and the radius of convergence is 1 from our prior work. Okay. And so all of these will have that same radius of convergence with the same center. Okay, so let's do A. If I wanted to find the integral of f of x dx, I'm going to integrate the terms of the series. First of all, I'm going to do it in a formulaic way with the sigma notation to integrate basically what would be 1 over n times x to the nth, where 1 over n is a constant, which can be pulled out in front. Forgot to say dx. The integral of that is, of course, raise the power by 1. So x to the n plus 1 over your new power plus c. Okay, this is just side work, which isn't extremely hard to do. So I did notice, though, I wasn't very careful. I didn't leave myself a whole lot of room. So let me go back and change something, which I should have thought of. Whenever you're integrating, you're going to have that constant of integration, and you want it in front, and I did not leave myself room for that. So I'm going to write that equal sign a little bit smaller and write c plus. Okay, and then the formula will become x to the n plus 1 over n times n plus 1. Okay. Now, what I'm not going to do is substitute in 1 to that, plus substitute 2 into that, plus substitute 3 into that, etc. That's not the way I wanted you to approach this. What I want you to do is to look at the first term of f of x and find its antiderivative. Of course, that's x squared over 2. Oh, and I did something else I shouldn't have done. I apologize. We don't know that this starts with 1 yet. So I'm going to erase that 1, and whenever I'm doing an integral or a derivative, I should leave that blank, n equals blank, until we figure out what it's going to be. And this is how we're going to figure that out. I was just ahead of myself. Anyway, plus, now we're going to look at the next term, this one, and find its antiderivative. And of course, the antiderivative of x squared is x cubed over 3 times the 2 that was a constant that was already there. And then the next one will be x to the 4th over 4 times the 3 that was already there, etc. Okay, so now this is where you figure out what n starts with. Looking at your formula x to the n plus 1, for example, what would you have to put in for n so that it would become our first answer, x squared? Well, obviously it would be a 1, right? would be a 1. And let's just double check the denominator. The denominator would be 1 times 1 plus 1. 1 times 2 is 2. That's correct. And then we put 2 in. We should get x cubed over 2 times 3. Notice I didn't write 6 or 12 as the denominator because it's easier to check what you should start with if you don't do that simplification. Okay. So we know that the radius of convergence, by taking the antiderivative of our series, will not change. Okay, so the radius of convergence is still 1. So, of course, that means that the preliminary interval of convergence, that means absolute value of x is less than 1. So our preliminary interval of convergence is from -1 to 1, and we need to check the endpoints. So let's let x equal -1. So that would be sigma of -1 to the n plus 1, and I let x equal -1 over n times n plus 1 is an alternating series. A sub n is 1 over n times n plus 1. Test 1 of the alternating series test. What is the limit as n approaches infinity of a sub n? And that's pretty easy to see. That's 0, and that passes that first test. Second test, what's a sub n plus 1? That's going to be 1 over n plus 1 multiplied by n plus 1 plus 1, aka n plus 2. And then we're going to compare that to a sub n, which is 1 over n times n plus 1. Okay, the denominator on the left is definitely a bigger denominator, which means that the fraction on the left is definitely less than or equal to the one on the right. And since a sub n plus 1 is therefore less than or equal to a sub n, that passes the second test, and we have convergence at x equals -1. Okay. Then let x equal +1. So our series will become 1 to the n plus 1, which is 1, over n times n plus 1, aka, I guess I could write this as 1 to the n plus 1, because I'm going to simplify anyway. That simplifies to be just plain 1 over n squared plus n. So one of the things that we did was, if I let a sub n for this be 1 over n squared plus n, and strip away lower powers of n, so take away the plus n, and that's n squared. And of course the denominator on the left is larger, so the fraction is less than. And then that could be my b sub n. And b sub n as a series is a p-series where p is 2. Therefore, or wait, since p is greater than 1, sigma b sub n converges. And because b sub n converges and the terms of a sub n are always smaller than that, and both a sub n and b sub n are positive terms only, then we can say, therefore, sigma of 1 over n times n plus 1 converges by what test? Direct comparison. See, I said you need to still know all of the tests of convergence and divergence. So it's not to be taken lightly. It's really important you know those. So that means, of course, that we have convergence at x equals positive 1 as well. And so that means that for the integral of f of x, the interval of convergence being initially -1 to 1, and finding that it converges at -1 and at positive 1, the interval of convergence includes both endpoints. So up here, remember our f of x, its interval of convergence was -1 to 1, including -1 but not 1. So we picked up positive 1 as a place of convergence in the integral of this. Okay, so part B is actually f of x, which we've already done. We did all that work up above, so I'm just going to report the answer that we got. It was -1 to 1, not including 1, and that's from prior work, all this work up here that we did earlier. So I'll just write by previous work. And the thing I'm wanting to see is that, or for you to see, is that the interval of convergence stays basically the same, -1 to 1, but the endpoints may be lost or gained as you integrate or differentiate. Okay, so C, we're supposed to find the derivative of that function. So if we take the derivative of the series formulation, this is n equals something, I'm going to remember this time, I don't know what that'll start at, of the derivative of x to the nth over a constant n is going to be bring the n down and reduce the power by 1 divided by the constant that was already there, because the constant could have just come out of the integral, and that simplifies to be n equals something to infinity, just plain old x to the n minus 1. Okay, so now what I want to do is I want to start with the first term of f of x. You may need to go up there and look at it again. If you're looking at the PowerPoint presentation slides, example 6, it's right there, but I'm going to scroll up here so you can see it. There's f of x right there, where I've underlined the first two in pink. So what I want to do is, we've done the derivative of that expression, and now what I want to do is I want to do the derivative of the right side. So the derivative of just plain x is 1, plus the derivative of x squared over 2 will be 2x over 2, which is just plain x, plus the derivative of x cubed over 3 will be 3x squared over 3, which is x squared, plus x cubed, etc. So, what would I need to start n at so that the first answer becomes x to the 0, which is 1? When I put in the second number, I'll get x to the first. So let's start there. To get x to the first, what number would you want to subtract minus 1? So what number do you want to start with so that when you subtract 1, you get 1? Well, of course, that means that for the second term, we needed n to be 2, so the first one, it needed to be 1. And of course, just to reflect on that, 1 minus 1 is 0, x to the 0 is the first term. So this would start at 1. And just to look at that, here n was 1, the function n was 1 below the sigma, and the antiderivative, it started at 1 as well. So actually nothing changed, unlike that theorem where it looked like you're supposed to change it from n equals 0 to n equals 1 when you do the derivative. That didn't happen. We didn't change n. So, like I said, you can actually just do the derivative of the formula behind sigma, and then do the derivative of the terms, the expanded version, and then just figure out what n you have to start with to produce that series of numbers. Okay, so again, we're starting with our interval of convergence being basically -1 to 1, because we're doing the derivative. And so to find the interval of convergence, we're going to test -1 and +1. All right, so our series would therefore be n equals 1 to infinity, -1 to the n minus 1. Okay, so what's that going to be? What's that going to be? Well, we could say that this is geometric because it fits that form. For the geometric, a is the in this case the understood number multiplied by that power. So a is +1, and r is the thing raised to that power, -1. And since the absolute value of that r is greater than or equal to 1, this series diverges. Of course, that's by the geometric series test, but since I already said geometric, that's covered. Okay, so that means it diverges at x equals -1. So -1 will not be included in our interval. We let x equal 1. That becomes the series of 1 to the n minus 1. Again, we can think of that as a geometric series where r is +1. I didn't really need the a because I wasn't going to find the sum of the series, but I just thought I'd show you what became of that, how it was actually geometric. Okay, and since, again, the absolute value of r now is still greater than or equal to 1, this series also diverges. Therefore, the series for the derivative of f of x diverges at x equals 1. And so we don't have either endpoint in our interval of convergence is -1 to 1, inclusive of neither endpoint. So in this case, if you're thinking about f of x and what happens to the interval of convergence, in this case we lost the left-hand endpoint from f of x to f prime of x, and we just have an interval of convergence from -1 to 1, including neither endpoint. Okay, so that's the end of this lesson, and I'll see you in class.